Hi, this is Mr. Barron. I want to talk to you about atomic structure basics. What you see up at the top of the screen are three of the models that have existed throughout the period of history where we have done investigations into what an atom looks like. This lecture is going to focus on just the basics of atomic structure, what the parts of an atom are, how big an atom is, and other various properties of what parts are in an atom. So the question that we want to answer by the end of this is, what are atoms and what are they made of? First off, we have to go back into history. We have to talk about philosophy to science. Greek and Indian philosophers were the first to postulate that matter was made of discrete particles. And we've talked about particles. That's a thing. It's just something very discrete, and it's an individual item. So one of these philosophers came up with the idea that the atom is indivisible, which means if this circle is my atom, I can't divide it into any other parts. That's one smoking hot atom. All right, so turns out these atoms themselves were made of even smaller parts, particles. So these philosophers were actually a little bit wrong, because what they defined as atoms actually do have parts that they can be divided into. All right, well, the model that we're going to be working with in this class is called the Rutherford model of the atom. And it basically is what you learned in middle school. And it's that the center of the atom is called the nucleus and has protons and neutrons. And then on the outside, in this cloud of electrons, are electrons which have negative charges. So let's talk about these parts of an atom. We call these parts subatomic particles. They're the parts of the atom. We have protons, neutrons, and electrons. And again, protons have a positive charge, neutrons have a neutral charge, which means no charge, and electrons have a negative charge. They each, if you look at the mass numbers, we basically, now remember, a mass number or an atomic mass number, let's go back to the periodic table and talk about those. The numbers on the bottom, below the elements in the periodic table, we call them atomic mass numbers. So one proton weighs one mass number, and one neutron weighs one mass number, an electron weighs nothing. When we convert them into kilograms, the kilogram mass for an electron is so small that we basically assume it's zero, that it's pretty much massless, but it does have mass. And the mass for a proton and a neutron are so close to one another, they basically have the same mass. So you want to basically think in terms of atomic masses, not in kilograms or grams, and that a proton weighs the same as a neutron, which is 1, and an electron weighs none. Don't forget, protons positive charge, neutrons neutral charge, and electrons negative charge. Now, how do we know there was that negative charge? Well, first off, we have to talk about a brief physics review here. The brief physics review shows that, remember the stuff that you should have learned in 8th grade, is that opposite charges attract. There's only 3 possible charges, positive, negative, and neutral. And a positive charge and a negative charge attract one another, and when they come together, they form what's called a neutral charge. You can think of this in terms of math. I mean, if you have positive 1 and negative 1 added together, then you get 0. The other thing to note is that like charges repel. So positive and positive push each other apart, and negative push each other apart. All right, wait a second. Logic time. Hang on. Atoms have negative electrons on the outside. Atoms coming close together before they touch would have negative and negative coming together. Negative and negative are like charges. Like charges repel. Wait a second. Do we ever touch? And this is not the time to go ahead and start slapping your brother or your sister in your home right now and saying that you never touch, but technically, no, we never do touch. Atoms actually repel each other just a small amount because the electrons on the outside pushing away on the electrons on the outside of other atoms. So if this is a picture that's a good example of it. So we have 2 hydrogen atoms, and the negative 1 repel each other. So technically, no, we don't touch. But it's so close, we can round it off and say we do. This does not mean you can go home and slap your sibling and say, Mr. Barron said we never really touch according to quantum mechanics. And that's actually the field that this is about. Quantum mechanics studies those really small particles of matter and how they come together and behave. All right, what about protons in the center? Why do the positively charged protons not repel each other and break the nucleus apart? And the answer is this thing called a nuclear force, and it prevents the protons from repelling each other in the nucleus. There's a lot of nuclear forces that hold the nucleus together, and we'll study more of those later when we actually talk about nuclear chemistry in this class. All right, let's talk about an atom. Let's imagine blowing up an atom to life size. If we blew up an atom to life size, the protons and the neutrons, imagine they're the size of a big truck. An electron would be this little baby sock, this little baby booty. So imagine you had to place the electron on the outside of the nucleus. Imagine this is hydrogen, and hydrogen has just one proton, one electron. So the nucleus would be really far away from the electron in terms of meters, but that doesn't make much sense to you guys. You guys think mostly in miles. So let's do some conversions here. It's basically 82 miles, 1,444 football fields away. That little baby sock has to be away from the big truck, which is the center. It's a long ways away. So how do we count these baby booties? I mean electrons, of course. First thing to remember, the charge of a single atom is typically neutral, meaning the protons and the electrons balance each other charges, or balance their charges out. Remember the previous slide where we talked about when positive and negatives are together in one unit, then those charges balance each other out, and then you're now neutral. That's what neutral means, is that your positive and your negative charges are equal to one another. All right, so let's take a look at two examples of neutral atoms. We have the hydrogen atom on the left with one proton and one electron. We have the carbon atom on the right with 6 protons and 6 electrons. If we look at both of them, the positive and the negative charges balance out. Overall, each atom has a neutral charge, which means it has no charge at all. All right, here's the key concept we need to walk away from with this lecture, is that what we have on the periodic table can tell us about how many protons, neutrons, and electrons are in an atom. Looking at carbon, what you see on the periodic table, the top is the atomic symbol. The middle is just the symbol. Sorry, wait. The top is the atomic number, the middle is the symbol, and the bottom is the atomic mass. The number of protons, which is the atomic number on top, determines who the element is. So that 6 up there, if I change that 6 into a 7, I can't keep it as C, it's now nitrogen. If I make it 5, it's now boron. If I make it 47, it's silver. If I make it 79, it's gold. The top number is the number of protons, and it's protons that determine what the element is, who they are, and what letter we use to represent them. Another way to write the symbol for elements is this format, and you'll see this in your book. The mass numbers in the top left, the atomic numbers in the bottom left, and then you have the chemical symbol or the element symbol, which is X. Now, let's take a look. We have this representation of carbon. It has a mass of 12 and an atomic number of 6. Notice how the 12 has been rounded off, because on the periodic table it's 12.01, and the atomic number is 6. So that if it's a neutral atom, that 6 tells us the number of protons and electrons, because they have to balance each other out in charge. The top number is the mass number, and remember how heavy an atom is. Remember, the electrons weigh nothing, the protons weigh 1, the neutrons weigh 1. So the mass number is the sum of the total number of protons and neutrons. So if I want to figure out the number of neutrons, I have to take the blue number and subtract it from the green number. 12 minus 6. It's an easy way to remember it. To count neutrons, you just take the bigger number and you subtract it by the smaller number. And the smaller number is always your protons and electrons if it's a neutral atom. One of the ways that we've discovered a lot of these subatomic particles is by experiments done by a lot of famous scientists back in the day. J.J. Thomson is very famous for having discovered the electron with a cathode ray experiment. A cathode ray tube is basically a television, an old television. We call them CRT monitors, the old televisions, and that's because they're called cathode ray tubes. That's what CRT stands for. When you look at this cathode ray, you see that it has a gas, and then you see this sort of beam in the middle. And that beam can be deflected or attracted with a magnet, and that's how J.J. Thomson was able to figure out that the electron had a negative charge, because if you look at the picture C on the right, if that's an electron beam, well, the reason it's attracting, remember, electrons are negative. Negative doesn't attract negative. It's positive that attracts negative. So the end of the magnet that is facing the cathode ray tube is positive, and then the beam is being directed upwards. So the evidence we get from the cathode ray tube, atoms contain electrons with a negative charge. This is the same way that a television works. It is, like I said, a cathode ray tube, and this is older televisions, not your plasmas or your LCDs. And it's an electron beam that is controlled by these deflection coils that basically vary the charge and aim the electron beam to hit a phosphorescent screen. And when that beam hits the phosphorescent screen, then it lights up and then you start getting your image. It goes back and forth, back and forth, back and forth. Now, let's talk about the old-fashioned models of an atom. Let's talk about how we got to this modern Rutherford atom. A plum pudding model is probably the oldest way. And it was an idea that there were these electrons canceled out by the sphere of positive charge. That's wrong. This is a wrong image of the structure of an atom. Rutherford, actually, Ernest Rutherford did an experiment to disprove this. There's a good animation on my website that illustrates this Rutherford gold foil experiment. I want you to view it after you've viewed this presentation. What Rutherford did in his gold foil experiment is he took some radiation and he shot that radiation at a very thin piece of gold foil. And he saw that the alpha particles, which were positive, and that's the type of radiation he was shooting, were being deflected and they were going straight through the gold foil. Most of them went straight through the gold foil. Well, why did most of them go straight through? Most of the radiation particles that were positive? That's because atoms are mostly empty space. Remember that electron? It's 1,444 football fields away. That's a lot of space for something to get in between the two. So he was the first one to realize that atoms actually are mostly empty space. The next thing, why did a few bounce back? Well, remember he was shooting alpha particles with a positive charge, and this led him to believe that, well, positive and positive repel, therefore the atom has a dense positively charged nucleus with protons. Remember, the nucleus is positive, the alpha particles are positive, are like charges, hence they repelled one another. How are atoms different from one another? Well, there are these things called isotopes. See, hydrogen is hydrogen because it has one proton. On the left we have protium, in the middle we have deuterium, on the right we have tritium. Each of those are a form of hydrogen. They're all hydrogen because they all have one positive proton in the middle of the nucleus. Now, what's different from each of them is not the protons or the electrons, but it's the neutrons. When the neutron count is different, we call them isotopes. And that's how you actually end up getting radioactive elements, is because they have really large numbers of neutrons in comparison to protons, and that makes them unstable.